Okay, we're not going to do a full curve sketching on this, but we're gonna do it like a real quick, rough curve sketch on this. The full thing, we're gonna find all of our x-intercepts, all the y-intercepts, all asymptotes. We're drawing a perfect graph. Here we can draw a pretty quick sketch just using the derivative. So first I take the derivative. That's 3x squared minus 6x minus 9. And I want to find all my critical points, literally for the rest of the semester. If you're working on a calculus problem and you don't know what to do, if you're just like, I'm lost, I don't know what to do with this, the first thing you probably want to try is setting derivative equal to 0. Because 99% of the time, that's the right first step. And that's what we're going to do. We're going to find our critical values by setting the derivative equal to 0 or places where it does not exist. This guy always exists. I don't have to worry about that. So 3x squared minus 6x minus 9 equals 0. I would divide everybody by 3 there. X squared minus 2x minus 3 equals 0. We are going to be doing so much factoring in the next couple of weeks. If you're not an expert at factoring, you got like 2 days to get there. You got to be quick at factoring. You got to, or you're not going to make it through the next couple of weeks. It's a lot of factoring. That's x minus 3, x plus 1. We get 2 solutions, 3 and negative 1. Make sure I got that right. Yep, that looks good. Okay, now there are a couple of different ways to do the first derivative test. What I like to do is a sign chart. Back in college algebra and pre-calculus, you learn sign charts. And if you did them using the factored version of your polynomial or rational function, these are so much easier. So let's put our values on here. I like to go in order. Negative 1 and 3. These were my critical values, where the derivative equals 0. This is a sign chart for the derivative. Okay, then I'm going to list all my factors, x plus 1 and x minus 3. I'm going to draw in this little table here. Oh, I totally missed that. Draw in this little table. And I'm going to figure out, what I'm really trying to figure out is this guy positive or negative? That's all I care about, positive or negative in each region. So one way to do that is just pick a test point. So think of any number that lives back here, any number less than negative 1. This is a whole number line here. So maybe you test x equals negative 2. So you want to know, is the derivative positive or negative in this region? So maybe you plug in a negative 2. You could even use the original version here. And what would you get? You get 6. Or no, you would get 4 times 3, that's 12, minus 12. No, plus 12, you would get 12 plus 12 minus 9, 24 minus 9. I think you would get 15. Don't really care what the number is. It's positive. So you could say your derivative is positive back there. That's one way, using test points. I'm going to show you a quicker way. The only way something can switch from positive to negative is by passing through 0. It's impossible for any function to switch from positive to negative without passing through 0. And the only place it can do that are at these factors here, at these roots that we just found. So all we got to do is figure out whether each of these factors is positive or negative in each region, and then we just multiply them together. So again, think about that test point, -2, back here in this region, -2 right there. -2 plus 1 would be -1. That's a negative number. I don't care what the number is, it's negative. -2 minus 3 would be -5. Don't really care what the negative is, it's a negative number. A negative times a negative is a positive. So this function right here, the derivative, is positive in this entire region. So positive everywhere back here. Positive derivative means the original graph is increasing. Okay, what about in this region? We pick any test point. Just make up a number. Anything between -1 and 3. So maybe you pick test point 0. 0 plus 1 . So I'm just plugging in 0 there. Would be 1. That's a positive. Don't care what the number is, it's a positive. 0 minus 3 would be -3. Don't care what the number is, it's a negative. Any negative times a positive is a negative. My derivative is negative in this entire region. That means my graph is going downhill in this region. So my graph went from going up to down. I've got myself a local max right here at -1. Okay, what about over here? Pick any test point, anything bigger than 3, anything that lives in this region. Maybe we pick a test point of 4, or 100, or 13, or 3, or pi, 3.1, square root of 12, anything bigger than 3. 3 plus 1 is 4. That's a positive. Oh, sorry, I made stuff up. My test point was 4. 4 plus 1 is 5. That's a positive. 4 minus 3, plugging in here, is 1. That's a positive. 2 positives multiplied together, because that's what they are, they're multiplied together, is a positive. The graph, the derivative is positive in this region. That means the graph is increasing. So I'm going from down to up. I've got myself a local min right here. Now, I don't even do the test points. I want you to notice something. I want you to notice that this factor, x plus 1, where did it switch? Just look straight across. It switched here at -1. It was negative on this side, below -1, and it was positive on this side. And where did this guy switch? Look across. He switched right here at 3. That's what's going to happen on every one of these. The factor, as long as it's to the first power, is going to switch over at the guy that makes him 0. 3 minus 3 is 0. His root is where he switches. He's always going to be negative before that and positive after, or vice versa. It's going to switch over at the place that makes it 0. So drawing these sign charts, you can do them in 5 seconds. He's going to go negative, negative, positive, switch at 3. And you'll see, I'm going to do a bunch of examples. You'll see the quick way to do these. You can always do test points, but you don't have to. And then an even number of negatives going up and down. Negatives cancel out when they come in pairs. So an even number of negatives would be positive. An odd number of negatives would stay negative. Positive answer is going up or increasing. Negative answer is going down or decreasing. Okay, let's do one more example in this video. This video might be a little longer. Okay, so I'm going to take the derivative. Every time, take the derivative. I'll get 5/3 x to the negative 2/3 minus 5/3 x to the positive 2/3. And I want to set that equal to 0. Okay, I would get rid of those 5/3, x to the negative 2/3. We could even move that over to the other side, equals x to the positive 2/3. Now we got to be careful here, multiplying both sides by our variable, but we could cube both sides. X equals 0 should be an obvious answer there. And then if I cube both sides, I'll get x to the negative 2 equals x squared. And then multiply both sides. Oh, now see, I got to be careful here. That guy right there is really 1 over x to the 2/3 power. I'm not allowed to use 0. That's a place where the derivative is undefined. So let's write that down. X equals 0 is where f prime is undefined. That's still a critical value. Now multiply both sides by x squared, or think of it as moving these over to the other side. You would get 1 equals x to the 4th. That has 4 solutions, 2 of which are complex numbers. The only real solutions there are plus or minus 1. So I've got 3 critical values, 2 where the derivative equals 0, and 1 where the derivative is undefined. Now, this one was a little more challenging. It's kind of hard to write the derivative as a bunch of factored linear terms. Here I am going to have to use test points. So I put all my critical values on here, -1, 0, and 1. And I picked test points in each region. I've got 4 different regions. So we'll call this 1, 2, 3, and 4. And I'm going to plug in x values into each of these regions. All I care about is, do I end up with a positive or negative? So maybe we'll get the calculator out for that. Okay, I'm going to be plugging in a bunch of x values into my function here. I could just do it one at a time, but I think it's going to be easier if we plug this guy into y equals, and then I can just use the calc evaluate to plug in different values. So I'm typing out the derivative here. 5/3 x. I need parentheses here to the -2/3, typing in the derivative here. Minus 5/3 x to the positive 2/3. I don't think I need the parenthesis there. Yeah, that should. Okay, then I can go second, calculate value. That's what my derivative looks like. Notice, look, exactly what I just said. It's equal to 0 at -1. It's equal to 0 at +1. And these are, like, you can't really see it in the graph. These are going to infinity. I have an asymptote there at 0. It's undefined at 0. And then I can just look at the picture here and see that I'm negative in this region, positive here, negative here. I'm looking up and down. All I'm looking at is, am I above the axis or below? So let's say we didn't have the picture and we were just doing this on a scientific calculator. Let's plug in a value back here, maybe -2. Look at that. I get a negative number. Negative. That means the function itself, not the derivative, the original function is decreasing. What if I plug in anything in here between -1 and 0? So maybe -0.5. I get a positive number. The derivative is positive in this region, so the function will be increasing. Okay, what about in this region? Maybe I'll plug in anything between 0 and 1, so maybe 0.5. I get a positive number. So the original function is still increasing. And then over here, plug in anything bigger than 1. So my critical values here were 1 and -1. So I don't know, 8. I don't care, anything bigger than 1. I get a negative number. That means the original function was decreasing. So I went from increasing to decreasing. I've got a local max right here, and decreasing to increasing, I'm at the bottom of a valley. The original function f has a local min right there. And there's something weird going on right here. It looks like some kind of asymptote. Okay, we're not ready for full curve sketching yet. So I'm not going to try to draw the original functions, but that's our goal here. That's where we're going with this. We're trying to graph that guy. Okay, that's a good place to stop on this one.